Hey, welcome back. This is the final chapter, final section in Calc 2. Congratulations for making it this far, I suppose. Just mark down in my notes where I'm going to make the video quiz so I don't always forget. Anyways, today we're going to be working with integrals, in particular the integral of polar curves. So we're basically finding the area underneath polar curves. I cannot find my video quiz question material stuff. There we go. Oh, it's sitting on the phone. Yeah. So this is the last question in homework 9. We'll be in here eventually. Okay, so anyways, first recall how we get the area underneath just a regular curve in the rectangular coordinates. Area. The section is called area of a polar region. But we'll begin by kind of revisiting our work with integrals in the rectangular coordinate system. So the spiel was we had some sort of curve, call it f of x or something like that, from point A to point B, and we want to know the area underneath this curve. So the idea was to split it up into a bunch of rectangles. Maybe have like a generic rectangle here, and all the way to the end. And we had some rectangle here at location x sub I. Its width would be change in x. A change in x sub I, if you wish, but the area of that one particular rectangle, let's call it a sub I. We got to smush that in. Okay, that did not go well, so let me. Oh, great. Okay, so this rectangle, I'm going to say is a sub I. The area of that rectangle from geometry, just base times height. Right, so it'd be f of x sub I times change in x sub I, if you wish. Okay, so there was some busyness back in that section about you being able to vary the width size. Okay. Anyways, the next step then was to take the sum of all those areas, so the sum of the a sub i's, and that would give you an approximation. Then if you took the limit as the number of those guys goes to infinity, you would get the integral, right? The integral from a to b of f of x dx. Okay, great. We want to accomplish the same thing now, but instead of working in this in the rectangular coordinate system, with our Riemann man is kind of running in this direction, collecting his bag of areas. Now the picture is going to be different, right? So in this case, we'll start off at some angle. Usually you start at 0, but you can start off at any angle. We'll just say angle alpha. And then we're tracing out the curve with its whatever the heck its r value is, maybe to some other angle beta. Okay, and we want to figure out the area underneath this curve. Okay, so the geometry is a little bit different, and not only that, the Riemann Man orientation is a little bit different as well. So for the Riemann Man, what is he doing this time? He's kind of like running around in a circle. Okay, that's kind of how I envision it. So he's kind of like this with his bag of areas, and he's looping around like this. Okay. So what are these areas that he's going to be collecting in his bag? Well, what we're going to use are sectors of a circle. Okay, so they'll end up looking like little pizza slices, right? So, we can approximate the area underneath this curve by using a bunch of little pizza slices. And let me fill a couple in here. And it's kind of the same construction except with pizza slices instead of rectangles. Okay, sort of butchered that one. And then dot, dot, dot. And then we have a generic one right here. and then dot, 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 all the way to the end. We have some guy like that. So instead of change in x, now you're going to have a change in theta. And instead of f of x, you're going to have f of theta. Okay. So in particular, let's designate this guy right here to be at angle theta sub I. Okay. And the curve that we're tracing out, let's give that curve a name. So we'll call it f of theta. This curve is f of theta. What else? The width of your particular pizza slices, basically from here to here, we'll call that change in theta instead of change in x. And for the geometric formula then, so if this one particular pizza slice, I'll put it in, I'm running out of colors again, so I'll put it in blue. I need a formula for that guy, a sub I. So where do I get the formula for these pizza slices? It comes from the formula for the sector, for finding the area of a sector of a circle. I'll just kind of draw that in here at the top right. So here's a circle, and I'm looking for the area of kind of a pizza slice of it that is designated by this directed angle theta. And so the area formula for the sector of a circle is kind of related to the area formula for a circle in general, pi r squared. Okay, the actual formula is 1/2 theta r squared. Okay. We know it's related to that. So if theta was 2 pi, you would get the formula for the area of a circle, pi r squared. Okay, so that's how it's related. That's where it kind of comes from. In our situation, with our picture, a sub I, trying to figure out, we have the 1/2, and then we have the theta sub I. The r value is going to be f of theta sub I. Okay, so then we have f of theta sub I squared. I apologize. It's not theta sub I. It's change in theta sub I, and for this theta. So let me adjust that a little bit. This part should be theta sub I, or rather, change in theta sub I. Okay, so at the end of the day, again, we want to send our Riemann Man around the circle this time and add up all of these areas and then take the limit as the number of little wedges goes to infinity, and we end up with our integral for determining the area underneath the polar curve, which will be 1/2 f of theta squared d theta, okay, from alpha to beta. Okay, one thing you have to be real careful about is this alpha and beta. And the alpha and beta, they have to be kind of within 2 pi. So just one note here, beta minus alpha needs to be less than or equal to 2 pi. Okay. Otherwise, you'll end up over counting the area. Because if you remember some of the graphs, we would kind of trace it out, and then if you kept tracing, it would just trace over itself. So if you were to integrate from some alpha to some other alpha where you go and over trace, you're not going to get area anymore. You'll get something else. Okay, you'll basically be doubling and tripling the area after a while if you go around the circle enough. So you need to be careful about that. Let's dive in here and try a problem. Okay, but at the end of the day, I mean, this is the formula du jour. The hard part, in my opinion, is just figuring out what is that alpha and what is that beta. Okay? And it's really, you have to be able, in my opinion, to graph these things by hand. So an example, find the area of one petal of a given rose petal. Okay, so find the area of one petal of r equals 2 cosine of 3 theta. Okay. Okay, so first I'm going to draw the thing and figure out the bounds on my angles for my integral. Okay. First, I go after my amplitude. The amplitude in this case is 2. Secondly, then, I go after my period. There's no phase shift. So I take this angle 3 theta and wedge it in between 0 and 2 pi, and then solve for theta by dividing all 3 sides by 3. Then I need my little tick marks. So I just divide that into 4 sections. So it'll end up being 2 pi over 3 divided by 4 or multiplied by 1/4. And of course, simplifying a little bit, we get pi over 6. And there's no vertical shifts or anything like that. So let me get my r theta picture going. I need to go up 1, 2, down 2. And I'm going by pi over 6s. And then 5, 6, 7, 8, 9, 10, 11, 12, just enough so I can get an idea of the bounds on the rose petal. Okay, so it's a cosine, so it starts up at 2 and then dives down and then dives back up. Okay, and then I'm going to get my picture. Okay. And it looks like I need 2 circles. And then my angular lines I'll be putting at pi over 6s. Let's put those in a different color, right? Well, no, let's just keep it at black. So pi over 6, basically 30 degrees, and then 60 degrees. And then one here about. Okay, so this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7, 8, 9, 10, 11, 12, or 0 if you wish. Okay. Okay, so I want to trace this guy out, and I'll start with 0 to pi over 6 is that region on the curve. 0 to pi over 6, it's going from 2 down to 0. And it looks like what we got there is like 1/2 of a petal. Okay, from here, if you wanted to, literally, you could kind of finagle your integral just via symmetry, but let's be a little more careful. Okay, so 0 to pi over 6 is that. Then pi over 6 to 2 pi over 6, it'll go on to the negative side of the arm. So from 1 pi over 6 to 2 pi over 6, it's actually over here, right? So it kind of curves over to here. And then from 2 pi over 6 to 3 pi over 6, it goes back to 0. And then from 3 pi over 6 to 4 pi over 6, it'll jump back to 2. Okay. And then from 4 pi over 6 to 5 pi over 6, it goes back to 0. And then from 5 to 6, which is right, it's kind of hard to see, it's this region here then, 5 to 6, it'll go negative again, so 5 to 6, it'll jump back negative. And then it looks like it's going to start repeating, right? So it's traced, the entire rows is traced from 0 to 6 pi over 6, which is the same as pi. We just need one rose petal though, right? So what I'm going to do is, well, you could do one of two things. You could say, all right, I'm going to integrate from here to here and then just multiply it by 2. Because if you integrate from there, from 0 to pi over 6, what you're going to get is this region here, and then you're going to be good to go. Another thing you could do is integrate from 0 to 2 pi over 6, and what will happen is that you'll get that little wedge there that I just shaded in, but you'll also get this wedge right here. Okay, and then combining those two wedges together, you'll get the total area. Okay. So whichever way you do it, I'm more inclined just to use symmetry and say, hey, let's integrate from 0 to pi over 6. that'll give us half the area of a rose petal. And then if you multiply the outside of the integral by 2, you'll get the other half. Okay. So again, remember the integral is 1/2 integral f of theta squared d theta. So in our case, this thing right here is the f of theta. Okay. So if I did not make that clear, the R formula, this R formula, whatever they give us, is the f of theta formula that you see in this formula in blue that I derived here in the beginning. Okay, so what do we have then? We'll have inside the integral 2 cosine of 3 theta squared, and then d theta. Okay, and the reason why I prefer this rather than, well, I guess it won't matter. So you could do that, but that's going to be equivalent to just integrating. Maybe it's easier, I don't know. Integrating from 0 to 2 pi over 6. I think they're pretty much the same integral. 2 pi over 6 is the same as pi over 3, and you have 2 cosine of 3 theta squared d theta. Those two are equivalent, but like I said, I'm more inclined to use the symmetry aspect of these rose petals. So I'm just gonna, well, I'll do the second integral as opposed to the first. Okay, so I'll work with this one just for, so I could do something different. All right, so let me go ahead and do that then. First square it, so I got 1/2 integral of 4 cosine squared of 3 theta d theta, and it turns into a trig integral, right? We could factor out the 4, so we get 2 integral, and then I'm going to use our identities to rewrite cosine squared, the reduction formulas, so that will be 1 plus cosine of then 6 theta all over 2 d theta. Then I'm going to, I can factor out the 1/2 from there, and you just get the integral of 1 plus cosine of 6 theta d theta. And then the integral of 1 is theta, the integral of cosine is sine. And if you do a u sub, you'll have a factor of 1/6. I'll just go ahead and put that there. And then I'm integrating from 0 to pi over 3. Okay, so I get pi over 3 plus the sine of 6 times pi over 3, which is just 2 pi all over 6, and then minus 0 plus the sine of 0 all over 6. And of course, the sine of any multiple of pi is 0, so we're just going to end up with just pi over 3, okay? Which is exactly what you would have gotten if you used the other integral. You would get the same answer, this other integral here. Okay, okay. Let's do another one. This one's a little harder because we're going to find the head of the snail. Okay, so this example, they want you to find the area of the inner loop of your limnosate. Find area of inner loop of r equals 1 plus 2 sine theta. So let's go ahead and try to graph this thing. So first off, the amplitude. It's just absolute value of 2 is 2. Secondly, then it's the traditional period, basically just from 0 to 2 pi. The tick marks, you can go by pi over 2's then. 2 pi over 4 is pi over 2. And then there is a vertical shift. Vertical shift. Looks like we're going up 1. Okay. Okay, so let's get a picture in the r theta plane. Okay, so originally with the amplitude 2, and we're going by pi over 2's on the theta axis. Five, 6, 7, 8. I usually just take tick marks all the way up to 2 pi, and usually that's enough to get at least one complete picture. Okay. Doesn't really seem that it comes up that I need more than 2 pi in the exercises that we do. Anyways, it's a sine function, so originally it looks like this. And then you take all those points and you shift them up by 1. So this point goes to here. I'm going to need another tick mark. This point goes to here. This point goes to here. This point goes to here. This last point goes to here. Okay. And a new picture. And you can see the head of the snail is where it just peaks down under the x-axis. I'll put that in blue. From here to here, basically. And that will pretty much tell you the bound on the integral. Okay. All right, so let me take a look at the picture and the xy plane. Looks like I need 1, 2, 3 tick marks, or 3 circles, rather. So 1, 2, 3, and then my angle lines, you can go by pi over 4s if you want. I'm just going to go by pi over 2s. So anyways, I guess I'll go with yellow. I'm starting at 1, and then it's increasing to 3 at pi over 2. So in this section here, start at 1 and then increase to 3. Okay. And then it's going to go from 3 back to 1 at pi. So 3, and then it decreases back to 1 pi. And then from pi to 3 pi over 2, which is basically this sector, the third quadrant, it's going to dip negative. So it's going to go to the negative side of your arm in this region somewhere. Okay. So it'll start out on the positive side, but then kind of go negative for the head of the snail. Okay, so let me start drawing that in yellow. So it starts out positive, but then it goes on to the other side of the arm and then loops around for this little blue region here that I've drawn in the theta r plane. I'll draw it in blue over here as well. It'll loop right there. Okay, that's to 3 pi over 2, and then it'll have the kind of same behavior as it rotates through the fourth quadrant. So it'll go back to 0, completing the head of the snail, and then it'll pop back positive and complete itself at 2 pi. Okay. So the region we want to integrate around is this blue region in the in either one. So it's the head of the snail, basically. So I need somehow to figure out what those points are. I know they're in the it's going to happen in between, here and here somewhere. I just need to figure out what those points are, basically this point and this point. So how do you figure out those points? Well, look at the graph. The graph is a graph of 1 plus 2 sine of theta. What does that thing equal at those 2 points? Well, it equals 0, right? So you're going to set r equal to 0. In other words, you take 1 plus 2 sine theta and set it equal to 0 and solve. Plus 2 sine theta, set it equal to 0, and you're going to get these 2 points where it intersects with the theta axis. Okay, so let's solve this little equation. I have 2 sine theta equals -1, and then sine of theta is -1/2. And inverse sine on both sides. Think about your unit circle and your reference angles. So the reference angle for 1/2 is pi over 6. Sine is negative in the third and fourth quadrant. So you're going to get 7 pi over 6 and 11 pi over 6. 7 pi over 6 and then 11 pi over 6. And you could use those as the limit on your integral if you want, or you can also use symmetry. So there's two possible integrals you could use. Basically 1/2 integral from 7 pi over 6 to 11 pi over 6, which may be kind of a nightmare to evaluate. If you're not all that familiar with your reference angles still. So it may be easier just to multiply 2 times, but honestly, I don't think it's going to be any nicer to kind of cut it in half, just so you can use that one angle, 3 pi over 2. It's not going to make your life much easier. Okay, but either one would work. The second one would just get half the head of the snail, and then multiply it by 2, you get the other half. Okay. All right. Let's just go with the first guy. Well, actually, in my notes I have the second one, and because I'm going to have to do a lot of computation, and I don't want to get it wrong, I'm going to go with the second one. Okay. So I'm going to use this integral. You could try in your notes to do the first one. And let's make this the video quiz question. Okay, so this will be our video quiz. You just have to evaluate this integral. And this will be our last video quiz question for Calc 2. It goes in homework number 9. So homework number 9 is worth 5 points. And let me just note in my notes, we're just doing this one integral. You don't have to draw out the picture and stuff. Just do the integral. And this will be enough of a nightmare. If you want to, you can do the other integral. As long as you get the same answer, I don't care. So this is 10.5. I'm just marking it in my notes so I know. Okay. Video quiz, video quiz, video quiz. Okay. Right, so the first part, it just get rid of the 2 times 1/2. So we have the integral from 7 pi over 6 to 3 pi over 2. Then on the inside, we have to FOIL 1 plus 2 sine theta. So that's going to end up giving you 1 plus 2 sine theta plus 2 sine theta is 4 sine theta. Then plus 4 sine squared theta, and then d theta, and then you can you're going to need to use the reduction formula on that character. So it's going to be integral of 1 plus 4 sine theta plus 4 times 1 minus cosine of 2 theta all over 2 d theta. And then that's going to be the integral of 1 plus 4 sine theta plus, and we can rewrite this as, 2 goes into 4 2 times, and then distribute the 2 to those. So you end up with 2 minus 2 cosine of 2 theta d theta. And then we can combine these 2 terms. So you always want to simplify your integral before you go and integrate. Sometimes on a test, I understand it's stressful and forget. 3 plus 4 sine theta minus 2 cosine of 2 theta d theta. Okay, and then we have something we can integrate the pieces of. So this will be 3 theta minus 4 cosine theta minus 2 cosine 2 theta over 2 if you do your u sub. Whoops, I mean 2 sine 2 theta over 2. But then the 2's will cancel and you'll just get sine of 2 theta. And then we want to evaluate these characters from, what did we say, 7 pi over 6 to 3 pi over 2. Okay, so let's see what we got. So 3 times 3 pi over 2 minus 4 times cosine of 3 pi over 2 minus sine of 2 times 3 pi over 2 minus 3 times 7 pi over 6 minus 4 cosine of 7 pi over 6 minus sine of 2 times 7 pi over 6. You see it's kind of messy. It's a good trig exercise here. So anyways, cosine of 3 pi over 2, that is going to be 0. So this part is 0. Sine of 2 times 3 pi over 2 will be sine of 3 pi. Any multiple of pi, the sine of that will just be 0. Okay. Cosine of 7 pi over 6. Okay, so that's going to give you a root 3 over 2, depending on the reference angle, or so depending on the quadrant. So 7 pi over 6 is right here. Cosine is negative there. So this part will be, this little half will be negative root 3 over 2. And then you still have the negative 4 you have to multiply by. The last guy is 2 times 7 pi over 6, which is going to be 7 pi all over 3. Okay. So it's, that's a radical 3 over 2 as well. We just need to figure out the quadrant. So 7 pi over 3 is 1 more than 6 pi over 3, which is 2 pi. So that would be just like 1 pi over 3. And our reference angle for that pi over 3 is going to give us positive square root 3 over 2. Okay, and you still have the negative in front. Okay, so let's see what we get. I have from the first term 9 pi over 2, then 0, minus 3 times this. So the 3 will cancel. You get 7 pi over 2. The negative, you have to distribute that. So you get positive 4 times negative root 3 over 2. And then again, you have to distribute this negative. So you'll get plus root 3 over 2. And then we can try to combine some like terms here. 9 pi over 2 minus 7 pi over 2 is 2 pi over 2, which is just pi. And then minus 4 root 3 over 2 plus root 3 over 2 is going to be pi minus 3 root 3 over 2, which is the answer. Okay? Okay, so that was the video quiz question for the day. All right, so they're basically trig integrals at heart. Don't forget to square that thing out on a test. A lot of people seem to forget the squared part. Just think pi r squared, that sort of idea. Anyways, let's go on to finding areas kind of between curves. So the idea from before, when we were figuring out these types of problems, you saw it in chapter 7. So what did we want to do? We wanted to find the area between these two curves, right? Or some variation of that from A to B. And you could do that just by subtracting them. So if that was F and that was G, this would be, after all is said and done, the integral from A to B of the top curve minus the bottom curve, basically. So it would be f of x minus g of x dx. Okay? In order to do that with the polar curves, so we can imagine some crazy scenario. So I'm going to draw like a 4-leaf clover type deal. Ugh. Then another 4-leaf clover. Kind of going like this instead. Let's say, for instance, we want to know the area. And you're working maybe with propellers or something. You need to know the area of these things, right? These little wedges. Oops, I don't want that one. I don't want the black ones. I just want Oh, great. I'm going to draw that thing again. I don't want this one. I just want those red ones. These guys. Okay, so the deal here is kind of just like the top minus the bottom. It's just the orientation of your Riemann Man is different, right? So before the Riemann Man is running along one of the axes. Now the Riemann Man is kind of going in a circle, right? So the top curve and the bottom curve is dependent on kind of where the Riemann Man is with respect to that circular motion. Okay, so in the beginning, if he's sitting right here at this angle, the bottom curve is the red curve and the top curve is the black curve. Okay. So if I wanted the area that I just sort of drew out there, I would need to kind of integrate from this curve, I'll call it alpha, to this curve, I'll call it beta. And in that little region, the top curve is the red curve. Okay, so you kind of just play it like you did before. You go the top curve, and let's give these guys names. Okay, so this the black curve we'll call f of theta, or maybe g of theta, just to be consistent with the other picture. And the red curve we'll call f of theta. Okay. Right, so we'll go from alpha to beta, and the top curve, like I said, was f of theta, so you have f of theta squared, and then minus the bottom curve, which is g of theta, so you go g of theta squared. It works. Okay, that's kind of the idea. Okay. So it's the same idea, it's just the Riemann Man is running in a circle collecting these areas. So the top curve and the bottom curve, you have to think with respect to now this circular rotation motion. Okay? And of course, if you wanted all four of those, you just multiply, because we found one of them, you just multiply this by 4, and that would give you all 4 of those little red regions, assuming it was symmetric, which it doesn't look like it's symmetric because of my poor drawing skills, but I intended it to be symmetric. In my brain, it was symmetric when I put it in. It's just a mess. Okay, anyways, one other thing that we'll need in order to figure this out, we need to be able to find the intersections of polar curves, right? So to find alpha and beta, I would need to know where f and g hit each other. And that seems like all you would need to do is kind of set f of theta equal to g of theta. Okay. The problem is this won't always work because of the way you can be on the negative side of the arm in your rotation. Okay, so we could actually be on the negative side for f of theta and on the positive side for g of theta, and if you solve this equation, you wouldn't get that particular intersection point. So usually what we end up doing is just kind of sketching it and then maybe getting our hands on one intersection point and then using symmetry to get all the rest of them. Okay, so let's delve into that issue a bit more. So this is now kind of a graphing area between polar curves. And the first thing we need to establish is how to get these intersection points. How do I find intersections? Okay, so let's look at an example here. And we have two polar curves, r equals 4 sine of 2 theta, which is some kind of rose petal, and then r equals 2, which is just a circle with radius 2. Okay, so you can kind of set them equal to each other and see what you get. Right? So that's kind of tried and true method. The trouble is we're not going to get all the solutions. But anyways, let's try. So I have sine of 4 theta, 2 equals 4 sine 2 theta, divide both sides by 4. You get sine of 2 theta equals 2 over 4, which is 1/2. take inverse sine on both sides, you get 2 theta equals, and then think of your unit circle, which reference angle gives you 1/2, that's pi over 6. So we have one sort of generating angle, pi over 6, and then the other angle in between 0 and 2 pi, and this is plus 2 pi n. The other angle that would give you positive 1/2 sine is also positive in the second quadrant. So the 5 pi over 6 plus 2 pi n. And then if you divide by 2, you get theta is pi over 12 plus just pi n. And then theta is 5 pi over 12 plus 2 pi n. Plus pi n. 2 pi n divided by 2 is pi n. Okay. Okay, so it seems like we got some solutions. Let's see which ones we have then. I have pi over 12, and then I'm adding up all the way to 2 pi. All right, pi over 12, and then 12 pi over 12 give me 13 pi over 12. And then plus another 12 pi over 12 would be 25 pi over 12, which is bigger than 2 pi, so I really only have 2 solutions there. And then I'll probably be retracing myself. Okay. From the other set, I have the 5 pi over 12, of course. And then if you add in 1 pi, you get 5 pi over 12 plus 12 pi over 12, which is 17 pi over 12. And if you add in another 12 pi over 12, you get 29 pi over 12, which is bigger than 2 pi. 2 pi is 24 pi over 12. So we have 4 particular intersection points. Okay. Let's see the actual number of intersection points between the two curves. Right. In order to do that, I kind of already know what this guy looks like. It's just a circle with radius 2. Okay, so I can plot that. This guy is a kind of a troublemaker, or I need to go through the rigmarole to get it. So let me do that. First, its amplitude. Its amplitude is 4. Secondly, then, its period is kind of smushed a little. So its period will just be pi. Then my tick marks, I'll be going by pi over 4s. Okay, so my little picture, 2, 3, 4, 2, 3, 4, I'm going by pi over 4s. Five, 6, 7, 8. I think 8 is good. Okay, and the thingamajig is a sine function, so it starts at 0 and then goes up to 4 and then back down. Kind of butchered this curve. Hopefully that gets the picture across to you as a student. Let's now go ahead and try to graph the thing in the r theta plane. I'm going to need 4 circles. I'm going to put these circles in blue because we're going to have 2 drawings. And one of them is a perfect circle, so it'll be going over my tick marks, or my concentric circles here, which are kind of like tick marks. Okay, so I start off at 0, and I'll put this guy in red. Okay, so I start at 0 and then go to, so I should put some little angular lines to help us draw. So pi over 4s, I'm going to put them in black. There's 1 pi over 4, 2 pi over 4 is 3, 4, 5, 6, 7, 8. So I start at 0 and then increase to 4 at pi over 4. So it's going to give me something like this. And then it's, whoops, I said I was going to do that in red. There it is. It's now in red, sort of. Okay, so that was this. then I'm going from pi over 4 to 2 pi over 4 in this region. So it'll decrease back to 0, finishing off one rose petal. Then it's going to go negative from 2 pi over 4 to 3 pi over 4. So in this region, it's actually negative, so you're kind of tracing it out over here. Okay. So it's going to increase to -4 in that direction. And then as we go in this sector, from 3 pi over 4 to 4 pi over 4, it increases back to 0. Okay. And then from 4 to 5, 4 to 5 is right here. Now it goes back to +4. Okay. So it's going to increase back to +4. And then from 5 to 6, it'll decrease back down to 0. So in this sector, it's going to decrease back down to 0. And then from 6 to 7, which is kind of this region, but because it's negative, you're actually plotting over in this region. It'll go to -4. And then I think we'll have the whole picture. And then it's going to increase back to 0 from 7 to 8. Okay, so it's from 7 to 8 pi over 4 increases back to 0. And then from 8 to 9, it would increase back to 4, so we'd be retracing. Okay, so we got the whole picture from 0 to 2 pi, or 8 pi over 4. Okay. Then let's draw the graph of our friend r equals 2, and then we can see how many intersection points there are. So I'll put r equals 2 here in yellow. 1, 2. Oops. And it starts at 0 and it just stays at 2. For any angle, the r value is 2, so you get this picture. And how many intersections do you have? You have 1, 2, 3, 4, 5, 6, 7. Oh, we missed half of them, right? So what do? You're just going to use symmetry to kind of finish out the picture. So the first one you see, this lower angle here, has to be the pi over 12. Okay. And then the one over here, I would say, is one less than the pi over 2, right? So 13 pi over 12 is right here on this side. So this one must be 11 pi over 12. So we're going to kind of put 11 pi over 12 here. And then what else do we need? We need this. We got the 13 pi over 12. We need this guy here, which should be right before pi. So we're thinking, oh, wait a second. So pi over, that would be 5 pi over 2, sorry. This one here is, 5 pi over 12, right? Because 6 pi over 12 would give you pi over 2, which would be right here. And then this one then is, so 5, 6, 7 pi over 12. We need, and then 7, 11 pi over 12. I apparently need, oh, I already had the 5 pi over 12, so I didn't need that again. Let me erase that. Didn't see that. 11 pi over 12, and then 13 pi over 12. I already got that one. That would have been this character right here. And then I need this one. So that's right before 3 pi over 2. So 3 pi over 2 would have been 18 pi over 12. So that's the 17 pi over 12. I already have it. Did I already get this one then? So this would be 12 pi over 12, and then 13. I got that one. Then I need this guy, which would be right after that 13 pi. Right after the what would that be? 17. So 18, 19 pi over 12. And then this last guy here. right before 24 pi over 12, so that'd be 23 pi over 12. And now I have them all. Okay. Right, so it's, you know, it's not as easy as it is in the rectangular coordinate system, unfortunately for us. Okay. But fortunately, most of these guys have so much symmetry involved, we can kind of just play that game where you go through and kind of collect your answers. Okay, so anyways, now that we have the intersections, let's actually find the area that is common to both of these regions. Okay, so the overlap between the flower and the circle. Okay, and I'm going to zoom in a little bit to make that picture clear. In particular, I want to just look at the first quadrant and kind of investigate what's going on there. So anyways, the ultimate picture that we want to find the area of, and again, you can pretend like you're working for NASA doing propeller design for drones or something. Maybe you're working for, I don't know, working for MI6 in Britain, and they need you to build a mini drone with a propeller that looks like this. They need to know the area of it so you can figure out the price for the materials. They use some special material for lightweight. So I need to find that area there. And it's an area between curves problem. You just need to figure out what's the bottom curve and what's the top curve and figure out the angles. Okay. So anyways, kind of zooming in to just the first quadrant, I'm going to need basically kind of the 4 parts of a circle here. 1, 2, 3, 4. Okay. And then that 1 is r equals 2, and I put that one in yellow. Okay. And then our other character, we'll go through pi over 4. Let me put the angle in black here. And we're drawing that one in red. Okay, so it's going to kind of go like this, and then like this, and then sort of go back and do the same thing. Okay. Okay, so your Riemann Man, remember, is running around a circle. So it's kind of like you imagine him, I don't know what color, let's put him in black. It's kind of like running around right here-ish. And for any angle, you kind of need to figure out which curve is on top and which curve is on the bottom. We want to figure out the area underneath in this region right here. Okay? And in particular, to find that region, I claim it's basically you're going to need that intersection point right here, because the curve on top and the curve on the bottom change right at that intersection at the pi over 12 mark. Hopefully you can see that. I put it in green. If you're green colorblind, hopefully that's not a big deal. I'm just running out of colors. Let me trace over it in a weird blue. Okay. So this is my pi over 12 angle here. Sort of highlighted it. Okay, so in kind of the first region, going from 0 to pi over 12, the curve that's on top is the yellow curve, and we want to know the area underneath the red curve, right? So we're kind of more interested in this region here. So in that first region from 0 to pi over 12, we're going to use the flower petal formula, okay, to get the area in there. Okay, so in that first region, I'm integrating from 0 to pi over 12, and of course it's 1/2 times this, and the formula for the rose petal is 4 sine 2 theta. And I need to square that, d theta. And then there's a second region, and then I'm going to use symmetry to get the rest. So the second region from pi over 12 pi over 4. In that region, we want the area underneath the yellow curve. Okay, so in that region, I actually want this area. And in that region, the curve that's going to give that to us will be r equals 2. Right? If you find the area underneath the curve r equals 2, you're going to get that blue region that I'm coloring in. So for the second region, we're going to use 1/2 integral from pi over 12 to pi over 4. And the r of theta, the f of theta is 2 in that case, so just 2 squared d theta. And we'll add those together, and what we get is basically 1/2 of one of these guys. We'll get like this region here, and then we'll need to multiply it to get the entire propeller. Okay, so 1, 2, 3, 4, 5, 6, there's 8 of those. So I need to multiply that sum by 8. So ultimately the integral will be 8 times 1/2 integral from 0 to pi over 12 of 16 sine squared 2 theta d theta plus 1/2 integral of 4. You can factor out the 4 times 1/2 is 2. Integral from pi over 12 to pi over 4. So hopefully that was kind of clear what I did. Okay. But I think as long as you keep in mind the top versus the bottom curve idea that we established here in Calc 2 in Chapter 7, hopefully you'll be able to kind of finagle your integrals. Obviously this wasn't like finding the area out here, which is kind of what I set up us to find. That's kind of a different scenario. So in that case, the rose petal would be on top, and you'd be subtracting away the circle area. It's a little easier of a problem. This problem's a little harder, I think. Okay. Okay, so anyways, if you evaluate that, you'll get your answer. So let's go ahead and evaluate the thing. And then we still need to talk about arc length here in a second. Okay, okay, so let's evaluate this. I'll go ahead and distribute the 8. If I distribute to the first one, it will be 4, and then times 16 is 64. I'll need to use the power reduction formula, so that's going to be 1 minus cosine of 4 theta all over 2 d theta, and then plus 16, and that will just be theta integrated. Factor out the 2, I get 32 times theta minus sine of 4 theta all over 4. And then I need to evaluate that, plus 16 theta evaluated. And then, so I'm going from 0 to pi over 12 here. So this will be 32 times pi over 12 minus sine of 4 pi over 12. 4 pi over 12 is the same as pi over 3, and then over 4. And then minus 0, minus sine of 0 is just 0, so that part will be 0. And then plus 16 times pi over 4 minus 16 times pi over 12. Okay, you can distribute this 32 eventually. Let's figure out sine of pi over 3 first, right? So pi over 12 minus pi over 3, sine of pi over 3 is root 3 over 2, so it's not being root 3 over 8, plus 4 pi minus, well, I need a common denominator here. I can divide top and bottom by this by 4, so we can have 4 in both cases, so 16 pi over 4. This will be, no, I can't divide top and bottom by 4. Well, I can, but then this would be, I want a common denominator of 4. Can't do it. So anyways, yeah, let's just get rid of this. Make this 4 pi. 4 pi minus, this will be 4 pi over 3. So what do we got? 32 pi over 12. I can divide top and bottom of that by 4. So that'd be 3. The 32 by 4 would be 8. So 8 pi over 3 minus 8 and the 32 is 4 root 3 plus 4 pi is same as 12 pi over 3 minus 4 pi over 3. That would be 4 pi over 3 plus 12 pi over 3 is 16 pi over 3, and then minus 4 root 3. Yay, that's the answer. Okay, okay, great. The last part then is doing arc length. So yet another arc length formula. We already had one from the rectangular coordinate system, then one from the parametric equations, and now we get another one, which of course you can derive from the parametric formulas. I'll just give it to you though. So arc length, we have arc length is equal to the angle from to the integral from angle A alpha to angle beta of the square root of your f of theta squared plus f prime of theta squared d theta. Okay, okay. So let's take a look at least one of these. Example: r equals 4 sine of theta, and we're going from 0 to pi. Okay. Okay. So I need f of theta, f prime of theta. F of theta is just the 4 sine theta. F prime of theta, then f prime of theta is going to be 4 cosine theta. And so it should be fairly simple. Throw it into our integral from 0 to pi, and we have square root of 16 sine squared theta plus 16 cosine squared theta. And we can simplify that using our Pythagorean identities to just be 16, square root 16 d theta. So that will be 4 d theta, 0 to pi, and that will be 4 theta, 0 to pi, that will just be 4 pi. Okay, that would be your answer then, and that will do it for me. Thank you for watching, and we'll see you next time.